cutting-edge knowledge. Please join me in welcoming Dmytro Minochkin for his talk. Compose locally, think globally. See you later.
Hello, everyone. Thank you for joining today's session. Today, we have Dmytro with us. He's a senior mentor at SoftServe Academy, and I hope that you enjoyed today's session with him. At the end of this session, we will have Q&A time, so you can ask him questions, and he will be responding to your questions. Please enjoy this time in the AI Week third session. This is a special moment for SoftServe and for all our partners to drive AI innovation around Colombia. So enjoy the session and be welcome. Thanks, Dmytro. I'll pass the word to you.
Hi, everyone. Just give me a sec. I'll share my screen. Victoria, can you stop sharing, please?
Yeah.
Okay, hopefully the button works now. Welcome to Colombia AI Weeks. Though I'm not from Colombia myself, but it's a pleasure to be here with you over basically from the other hemisphere. What we're gonna discuss today, the title of my talk is called Building on-Device LLM Apps with Kotlin, Compose Multiplatform, and llama.cpp. And the subtitle I decided to give it is The Art of Misleading Titles, because that's not the only thing that we'll discuss today. Just a few words about me. I've been in programming for quite some time and basically started as a Java developer, as most people usually do. And I was working with Android and a few other technologies. From 2019, I'm toying with Kotlin Multiplatform. Because Swift UI became a thing and I decided I need to know it. But later on, mobile became my passion, and in my day-to-day work, I'm usually involved in cloud technologies and AI. I'm gonna have a talk about a mix. So we'll discuss mobile development, but with a spark of AI. Here are my misleading titles. So we will have three topics today that we'll discuss. Basically, an introduction of the current state of AI on device. We'll discuss how we can write C without writing C, because you can do multi-platform without C yet, but we'll see how you can move around it. And we'll discuss what next. Well, if we have a LLM that runs on device, maybe we can build something with it. So for the intro, let's discuss the current state of AI on multiple platforms. And basically, hopefully you know that we have quite a lot of platforms. Well, basically iOS, Android, web, some desktop things, and even IoT devices. And some of them, or even all of them, probably need some apps with AI. I dread the day when my fridge will scream at me for not closing the door, but even IoT devices can have it. And for us as developers, our goal is to deliver products to a wide range of customers on all of those platforms. Well, technically, in our world, when we talk about like desktop, for example, or even mobile, web development can take over, like with progressive web apps, WebAssembly, like even the GPU support with web GPU. So technically, you might not need anything except web sometime soon. But in general, if we are talking about on-device things, people might prefer a native app or semi-native app that works on-device without connecting to a browser. So what's the state of AI or inference rather on those platforms? Well, currently, there are a lot of frameworks, well, not a lot of, but a bit, that exist that allow us to run AI inference or Gen AI for that matter on device. Some of them are, well known, though renamed, like Light-RT, which was known as TensorFlow Lite. Then there's like a Torch, ExecuTorch, and Microsoft ONX runtime. And well, the thing is, not all of them support all the desired platforms, or they do support it in different ways. They have different model formats, different approaches, and even within a single framework that we use for mobile inference, it is hard to do code sharing on high level. Like, for example, if you wish to share code between Android, iOS, and any kind of desktop or even web, you will need to write separate copies of the code anyway, because libraries are rather, well, platform dependent. Especially, for example, Light-RT that comes with Google services, so you can't even run it on maybe older devices that can support inference. But yeah, maybe slow, but still can support it. So when Leon proposed to participate in the talks, I decided like, okay, let's explore something that is fun. Well, yeah, if we must go to C, let's explore something pure C without all the hassle. And well, basically llama.cpp became very popular this year. And yeah, the main guest for my talk will be how can we leverage llama.cpp with modern tools to run AI inference on device. So yeah, I know that not all of you are, well, mobile developers or C developers for that matter. So through some of the slides, I will have emotional support. So some cute anime girls will just try to make this a bit more chill. So yeah, if you know mobile or C, you can even help me with some things. So yeah, let's dive into introduction to llama.cpp. So yeah, llama.cpp became very popular this year, basically starting through early August. And that's not me Googling about like what llama.cpp is. Yeah, just I have added this slide to know that yeah, it was a release of some Chinese models that got support in llama.cpp that was like this boom of activity. But still, if we see comparison to other platforms, it is well, kind of semi-popular or a bit more popular anyway. Well, once again, Microsoft ONX runtime also became a bit popular this year. But still, yeah, today llama.cpp looks like a good choice. And why it is a good choice, except it allows to run GPT OSS and Llama on devices, well, not mobile, but still. So what good things it has? Basically, in its design, the developers thought about llama.cpp as a library that would allow us, or a set of tools rather, run inference for large language models on consumer devices. So basically, even without the available backends, you can use anything that has a CPU, well, semi-modern CPU, to run inference and get the modern technologies on, well, even a toaster. But if you don't have a toaster and you have a set of GPUs, well, basically llama.cpp has got you covered. So all the modern technologies that exist, starting from Apple Silicon and ending with NVIDIA and CUDA, are supported, well, in a way, even with multiple libraries and APIs. And right now, there's an active development of web GPU support. So probably, yeah, if I get ever invited next year, we will discuss how to do it for the web. So, but today we will skip it, but still it would be fairly trivial to add when we know what needs to be done. So yeah, what other good things or semi-good things are offered with llama.cpp? First of all, as all the frameworks that exist, it has its own model format. The current model format is called GGUF, or GPT-generated unified format, and it's basically a single file package that has everything you need to run a model. So basically, it has the model itself, so weights and tensors. If you've done some quantization, it can have the quantization layers. Then you have a tokenizer packaged, so you don't have to find some tokenizer for a given model. It comes in the file, and some metadata that you can use and read to understand what's going on inside the package. So as for quantization, and as we're talking about on-device and mobile phones or laptops, we can't run. Yeah, there was a question in chat. What is a quantization layer? So basically, what is quantization in general? Most models are trained using a float32 floating point operations. But in general, this is very expensive in terms of memory usage and for inference, rather. And quantization allows us to basically cut the numbers we use. So instead of like high range floats or even bfloat 16, we can come down to integers. Like, for example, we do only integer operations and for llama.cpp, we can do like from very small 1.5 bits per integer to 8 bits per integer. This will make inference or our model a bit, as you can say, lobotomized. Like it will not work as at its full potential, but still it can be utilized, and the benefit of having a smaller memory footprint and well, basically, yeah, smaller size can have its own advantages. So on top of all these things, like you don't have to do it by hand. So in Llama C++, you have basically all the set of tools you need to do it. Like you have a CLI to run things. You even have a server if you need to. So you have the quantization tools and a lot of other additional things you can use, install, and run models. So yeah, once again, for when the GPT OSS was released, people already were running even that large model on their device as well. Mostly servers and desktop computers, but still it was possible. So once again, GPT OSS is not the only model family supported. So another good thing is that currently llama.cpp has a large count of models that it supports, and basically this is official support, so it means it will work for sure. And there are some maybe less known models. Well, I didn't put Mistral as a bold model because I haven't worked with it. But yeah, for me, Meta, Google, and Microsoft and Qwen models are more familiar. And still, yeah, those are popular. There are a lot more, so more than 75, and this is an official count. So even if the model is not supported officially, technically, if you convert it in the GGUF format, you have a high chance to run it. And well, basically, Llama comes as a first-class citizen. So it was first developed using Llama models. And so, yeah, all the Facebook series models are supported out of the box. But text only is not the only possible option. So there are some multimodal models. Once again, these are some kind of, well, at least Google shows them. I haven't worked with them, but some models are not here. For example, Gemma 3 multimodal is not here, but it is supported if you wish to run it. So it is the official count, but as I said, it can be more than that. So what are other good things? So in general, it is not a high-level framework that is offered by like Microsoft, Google, and the others. Basically, it's a set of tools and, well, high to low level methods that you can use as Lego. So you can build your own machine learning inference the way you want it. So if you wish, like you can slap one thing, add another thing, like do some things your way. And another good thing is that it is written from scratch almost. So it has minimal dependencies from out of source libraries. So one optional is curl to download the models if you run the CLI. But yeah, it's not required, as you can load the models yourself. And yeah, it makes this library very small or even tiny compared to other technologies. And once again, as it does not depend on anything else, there are no prerequisites that you should have. Like, for example, for LightRT, Google has a very good application that is called well, I forgot how it's called. I think it's called AI Gallery by Google Research. And for example, it works on my newer Android phone, but doesn't work on my older phone because, well, reasons. And llama.cpp works and does inference easily. So yeah, it's great. So a lot of good things we have here. But are there any bad things? Probably the only bad thing is that this library is still evolving. Like it is not a final product. And basically you can have more than 200 commits per month that add new features, fix bugs, etc. And it becomes a problem if you wish to use it because bindings that exist for various languages became stale or rotten very fast. So yeah, they might not fix bugs fast enough, or implement other features that once can improve your day-to-day life. So yeah, here are some libraries, at least that could concern us. Well, basically Python and React Native are the best supported, but they are not, or they cannot be applied to us because, well, Python can be used for mobile development. Well, I would rather not. And for React Native, it doesn't support desktop in a way I wish it would, and the bindings are only Android and iOS. So yeah, once again, it will not work for us, but the others that can be used are also either very old, and here 2 months is very old, for example, or just a wrapper over a wrapper, which doesn't cut it. So once again, how do those wrappers work? And I will discuss the React Native wrapper because once again, out of all the presented wrappers for mobile, it is probably one of the best written ones, but it has some issues because we can't use it. So what are the issues that we technically can copy, like some of the bindings did, but we will know if we should do it. So yeah, for React Native bindings, they have, well, this kind of simplified architecture. So they have a wrapper over the C code that they use to basically invoke the high to low level llama methods. And also, well, once again, that I also did a bit because my PR has not been accepted to llama.cpp yet, and I don't know if it would. So yeah, they heavily patch the library to fix some things that for one or another reason are not fixed in the main library, because for now there are almost 500 or more than 500 rather pull requests open. So yeah, some things might not get inside fast enough. But yeah, they have one fat wrapper, and on top of that, they have two distinct wrappers that are platform specific. So for Java, it's Java native invocation C wrapper. And for iOS, it is a Objective-C wrapper. And then they have some platform-specific code that in general leads to high-level bindings that you can use in React Native, if you wish, and even in pure Android or iOS applications, because, well, you can. But once again, there are a lot of things that probably we should not use or are not needed for simple inference if we wish to build a AI-powered products. Once again, they might be needed, like they can improve either performance a bit or make it do some other things except pure inference. But once again, their goal here was to create a complete binding to cover the entire surface of the library. But it is actually not needed because, like, do you think we need 5,000 lines of C code to run inference, especially if, once again, everything else is written by llama.cpp, so you don't have to actually do things. And once again, this was my thought when I decided to investigate how can we solve this problem. And what is the solution? Well, technically, the only solution that exists is to write our own binding so we can reinvent the wheel. But for making an AI-powered product out of, well, more than 200 methods that exist in the Llama library, we actually need around 25, well, maybe 27. And the rest is just optional things that can be used. Like, it's not bad that we use it, but we can gradually add additional features as, for example, a product evolves. So yeah, what it means for developers, it means that we need to write some C code, or should we? And this leads us to a second portion of my talk, which is called, yeah, it's C until it isn't. So yeah, what does it mean? Is that we technically can write C code without writing C code. But first, once again, I will pause my sharing for a bit so we see if I can interest you with a little demonstration. So yeah, just give me a second. I will stop sharing on this device and just hide my camera for a bit because I will need to switch to another computer, but I will be here. So what we'll do, I'll do a little so hopefully you can see my other screen and you can see what's going on. So technically, UI is not going to be part of our talk today, but in general, we can see what llama.cpp can do on a consumer device. So here is my Windows machine because it has NVIDIA graphic cards, and NVIDIA is a sponsor here. Like, they did not buy me a graphic card, but still. It's better to show this because the metal acceleration I can show a bit later. So yeah, we can do and select a model. Let's say we choose a mobile model which eats less RAM and run it on CPU. So let's try something. For example, tell me a story. So it thinks a bit and it does inference purely on CPU. Well, as we can see, the iGPU kicks in, but most of the work is done on the CPU, and this is what llama.cpp does great, because it allows you to utilize consumer devices that probably do not have powerful GPUs. So we'll give it a few seconds. Yeah, it will finish generating a fun story about Labubus, and we'll give it a shot with some other things. So as you can see, yeah, my CPU might be a bit more powerful than an average mobile device, but still the inference is, well, not great, not terrible. It's fast enough, maybe like ChatGPT does it. Though there are, as you can see, some emojis that were not rendered correctly on Windows, but it's not an issue. So let's do something more interesting, and I will just slap off this model and I will just enable the GPU. So yeah, I'll just pick, let's pick the same model, but here we can even pick a bigger model that is an 8 billion model, but I will just want to show them a model in action or GPU in action. And once again, this is what also llama.cpp does best. It allows us to utilize any kind of backend it needs. So here I baked the Vulkan support, so it can run on multiple GPUs, at least, hopefully. And yeah, let me clear the chat and let's see what llama.cpp can do. Yeah, okay, I can write, yeah, no. So, and with GPU kicking in, it's a bit faster and it doesn't take any CPU time, but the iGPU kicks in a bit more, and we can see the same kind of story was generated a lot faster. So yeah, let's see. We have seen it in action, so let's see how we can build this thing from scratch. Once again, I will show my code a bit, because once again, it is not 5,000 lines of code, but yeah, still there's some things to do. And we might not be able to see it all in real time today, but I will share and push the repository and you can explore it at your leisure later on. But yeah, always when you show a demo, you have a question if it works on my device and will it work on your device. So if you wish, once again, I have not done the hardest part of software development. I have not passed Google and Microsoft review yet. So once again, it should be done by the end of this week. But yeah, thanks Apple. If you wish to run this little application and play with metal acceleration on your Apple Silicon, you can scan the QR code or, well, technically, yeah, I forgot to copy it. I will probably do it just now and throw in chat. Once again, you can install the application, play with it and see what you can do. So, but yeah, this is just a side note about actually performance of llama.cpp. And let's check. Yeah, just give me a second. I'll throw in the link once again on the App Store. So yeah, let's move on and discuss what can be used to write C without writing C. And here Kotlin can help us. So what is Kotlin? Kotlin is a programming language developed by JetBrains company. And you probably have heard about that company. They are very famous for doing IDEs. And well, they had problem with Java, as all people do. And they invented a new language that should have done some things that Java can't. And when the language evolved, they decided if they can compile this language to Java, why not compile it to other binaries, or rather bytecode formats, to be correct. So once again, what is Kotlin multiplatform in a nutshell? It's basically an approach that differs from other frameworks like React Native or Xamarin. Well, Xamarin is that, it's MAUI, I think, or Flutter. Basically, their philosophy is not share the UI, but share business logic. Because native UI works best and it's not actually required to share it. So it allows you to build and compile your common Kotlin code into any, or well, bytecode format, because JavaScript is not a bytecode format, but still, yeah, you can compile it to native code and run native executables on your device. You can compile it in Java code, run it in the JVM environment. So you can support all those 3 billion devices that that use Java. Or yeah, you can even target web. So yeah, my first slide was when I said that the web is taken over, you can take over it with Kotlin. So how do they do it? Well, basically they have the compiler that allows you to basically write common code, and that code can provide interfaces for platform-specific operations, which is called the expectations for some platform implementation. And then you can implement those interfaces per platform, but then inside your application, you speak the common code. And when you compile it to well, let's say native binary, the code that you implemented per platform joins with the common code, and you basically get a native experience without all the hassle. And so, yeah, once again, it is used to compile applications to different targets, right? But how can it help us to not write C? One of the cool features of Kotlin multiplatform, or rather Kotlin native side, is, or well, any Kotlin targets, is native interoperability with the platform that is being used. So, for example, on JavaScript, you can interop with JavaScript, like call JavaScript code from Kotlin. Well, in Java, you can call Java from Kotlin, and on native, you can call C from Kotlin. And compared to React Native and Flutter, that all have some kind of native operations, Kotlin has a bit more automation to it. So it just scans the headers you provide, generates stubs and wrappers for your Kotlin code, and you basically call C code as Kotlin methods within your native environment. And yeah, just it. In the end, you can compile a binary to, for example, a native executable that will have both your Kotlin code that has all the rich features of that language, and you can use any kind of shared library that your system has inside. So what else it offers that can help us do the magic? Well, as it is a higher level language than C, it can allow us to automatically manage memory that most people, well, I mean, C developers like it, but manual memory management is probably not a thing you imagine doing once again day to day. So to interact with C, Kotlin has a memscoped blocks that basically allow us to allocate native memory, use the pointers and other things, and automatically clean the memory after exiting the scope. And even exceptions are not an issue, so they will anyway clean the memory, and you can be sure that you don't have any memory leaks in your application. Well, especially if we're dealing with LLMs, yeah, having a memory leak with a few gigabyte model may be a problem. What else it can do? Well, technically, another cool option is that you can throw some Kotlin code to the native code and back. So the option is called stable references. So for example, you can create a class in Kotlin, or Kotlin native rather. And here as an example, like if you wish to log something from the native side, for example, llama.cpp has a possibility to substitute a login callback. So you can create a Kotlin object, wrap it in a stable reference so it does not get garbage collected because it is not used in your Kotlin application, and throw it through the C boundary. And yeah, basically you can have a cross-platform, or rather native logging written in pure Kotlin, but used in pure C. So how does it help us basically build a thing that we wish to build? So as I said, Kotlin allows us to write a common code, and with it, we can only implement some platform-specific things with, well, basically native code if we wish. And for a project structure, Kotlin multiplatform follows a hierarchical approach. So technically, you have a root of the hierarchy, which is called common code. So this is the code that can be shared between multiple platforms. And then you have this tree of different options you can go. You can go to web, you can go to Java machine, you can go to mobile, or you can go to Apple. And once again, oh, sorry, not Apple, but you can go native. And inside native, there's like a subtree of different solutions. And anywhere in this tree, for example, you can implement something here and then maybe expect something here, then implement it on native side. For example, if you don't wish it to be used in the all native targets, you can, for example, implement it only in macOS. Well, that way you will have to implement it like in all the leaf nodes, but still it is possible and allows you to basically scale your code from different directions. And it can allow us to, well, basically build a wrapper that doesn't use as much C code or any C code rather, and still be productive. Okay. If we're talking about native wrapper, then it's simple. We slap some Kotlin native code and it just works. And yeah, technically for llama.cpp wrapper, you just press play button. Well, I'm just kidding. Yeah, it you have to do some other things, but in general, yeah, you just execute the binary and it works. For web and JVM, it's not so simple because you can't use C libraries directly in Java or web code. So for web code, you will need to use WebAssembly, and WebAssembly only like came out to beta from alpha a week ago for the UI part of the application. So I have not slapped it on. So today we're not talking about web. Okay, we have a question. Yeah, there was a question if it is possible to run GPT OSS. Yeah, it's possible. There are benchmarks on different, well, at least they have run the 20 gigabytes model, the one I read, because there's a huge thread on GitHub discussions. But yeah, it is possible. People have used the llama.cpp server that comes as part of the application, part of the toolset, and they have run it on their own desktops. So yeah, it is possible. But yeah, coming back to the question, okay, we can easily build a native wrapper with less code than it could have taken us with a pure C implementation. But yeah, for JVM and Android, we can't do that because for JVM and Android, as I said, we can't interact directly with native code because, well, it's Java machine. But there's a thing that exists, which is called GNI, so Java Native Invocation. So basically, it allows us to build a special set of headers and C wrappers to allow JVM to call C methods. So technically, it leads us to, well, the beginning. So for JVM, we will have to write some C code, or do we? So once again, the power of Kotlin Native is that it allows us to first automatically generate all those pesky headers that can be used for GNI, if you wish. But, well, it still will require some manual work to handle all the things that GNI adds, like, for example, manual marshalling of objects between the native and JVM boundary. So what we can do, well, as all the bulks of inference will be done by native code, and here I mean Kotlin native, we can use, for example, a lighter wrapper that can automate some things. Once again, so I might not have given all the, or drawn rather all the lines in the correct places, but technically, how can we simplify the binding of llama.cpp for all the platforms? Well, except web. So we can implement the bulk of inference with a set of Kotlin native methods. Then we can directly feed it to native platforms. So for example, iOS can just leave it at that. And for Java, we can have a basically not GNI, not Java native invocation, but GNA approach. So GNA, which is called Java Native Access. And this is a reflection-based library that is widely used in Java community because, well, it allows you to not write C code. So here for JVM, once again, we have a scene library that consists of a small interface that just calls native methods for you. And it all just is wired by common code that we also can write. So yeah, it is still double wrappers because, well, JVM is an issue and you can't go around it, but still it is not tens and thousands lines of code. And yeah, a question for you guys. How much code do you think have taken me to write this inference? Or lines of code rather. Any wild guess, maybe? You can write in chat if you wish. Probably Manuel has some psychic powers. But yeah, well, it's not 1,000 and it's not 100. Basically, with all the comments and new lines, yeah, it is around 1,000 lines of code. But in general, if you just compact it, remove all the comments and to-dos I left for myself, you can do it in around 300 lines of code. And once again, on top of the minimum required 25 methods, I added some logging, I added some like device discovery, and you can write it in actually, well, yeah, around 300 lines of Kotlin native code compared to running 5,000 lines of C code, for example, for React Native. And once again, a bit later, I will show you how it works. But yeah, once again, what are the caveats for, let's say, using this approach? Because, yeah, nothing comes without a price. Well, first of all, yeah, the first price we have to pay is, once again, if you don't want to write more code, and I really don't, because once again, I have written enough code already. So GNA helps us, but it costs us performance. So it is a tool that allows us to not write code. It will be done by reflection. But it is, well, due to reflection, it is around 10 or more times slower than pure C written GNI. But once again, as we're not doing any memory management in Java, we will be only calling the native side, for example, like to return a generated string from the LLM. The price we pay, or like the rather slower execution of throwing a string across the native Java boundary, is a thing we can manage because the bulk of time the C code will be responsible for the heavy duty operations. So the easier maintenance and well, maybe not easier debugging, but still not writing any code and just slap an interface with 20 lines of code, well, technically, would be enough to cover the Java side. But once again, it's not the only thing we have to pay because we can't directly use nor GNI and and not GNA with Kotlin native shared library. Why is that? Because the library is not exposing any headers that we can use and bind to our GNA. So what we need also to do, well, yeah, we will need to have a little bit of exporting. So basically, we should ask Kotlin nicely to say generate some C headers that can be used by other well, native or JVM platforms, and it will do it. So in general, what it allows us to do and how can we simplify the crossing of the Java and native boundary. So basically, well, this is a simplification that we should follow. We should not throw complex objects or functions or anything like that across the Java native boundary. unless we really need to. So basically the communication should be in simple types. So for example, here is an example of loading a model. So we don't need to know or have a complex pointer to the model on the Java side or the Kotlin part of Java. We only need to know if the model is loaded. So the heavy-duty operation goes through all those interfaces that are basically, well, 1 or 2 lines of code, reaches the heavy-duty Kotlin native method, and that method loads the model, returns the result, and on the Java side, we know that the model has been loaded. So as we need to wire it up with common code, so basically all the interface of the common code should also speak in simple types, which is not an issue. So once again, in a little example, how we can use it, yeah, I have it here in my project. So once again, one intimidating thing with Kotlin native development is the amount of sub-projects or other source sets you will have when you try to develop for multiple platforms. So in my hierarchy here, I have a common main source set that has basically all that is required and to run, well, or rather speak with the model from any platform. So it has a interface that, well, I have not written much comments, but in general, it has a simple interface that allows us to load model, for example, generate text and do some other things. And basically, the interface is implemented in a way that all it does is that it delegates this to a platform implementation. So what is a platform implementation? Basically, platform implementation is what drives this magic inside. So if I just fall inside, once again, platform implementation has the same methods, but those methods will be implemented not in the common side, because we have the expectation, we have a function that allows us to implement this function not in the same code base, but we need to implement that function in some other source set in the hierarchy that will lead us to the final binary. So how can we implement it? I have 2 implementations. So the first one we'll see is the native implementation. So this native, sorry, not native, but Java implementation. So the only thing it does, it has a pointer to the Kotlin native side. So basically to the shared, to the object we get from the shared library that we have. And inside it, if I have the structure here, we have some implemented methods that, once again, just delegate everything to the underlying C code by just using a bridge GNA library. Once again, it is some overhead that I can pay because this is only, once again, 200 lines of code in general. And yeah, it can be like a copy paste and some methods called. So what is a bridge library? This is the GNA bridge. So it is a simple interface that can be used through reflection. So once again, this is all pure interfaces that automatically wire together. So the most interesting part comes from Node.jvm, because this is a simple wrapper that takes a shared library, slapped in runtime, and just uses it. So the most interesting thing comes from the native implementation, and basically, yeah, this is what we get. So first of all, yeah, some bridging, and once again, this is not tens of thousands lines of code. This is basically exporting some C headers with some functions that do, once again, calling of the native methods we have created in Kotlin. So yeah, once again, we have not 3, but like 4 wrappers, but they are very thin and they just allow us to communicate between platforms. Because as I said, for native, like for example, for iOS, you don't need anything. Like you can slap Kotlin native code inside the Apple framework and it can be used as is. and yeah, you can use inference without all the hassle. So all of this is just needed to for JVM and Android to work. And once again, as both Android and JVM shares the same platform, well, as a Java machine, we can do it in a single place and just reuse it. So once again, how do we do the native calls? And just let me find the platform implementation. So yeah, basically we have an actual implementation of the function that returns us the native part of our application. And once again, in common code, when we build native, this is used by default. And when we build Java, we have a wrapper, once again, that hooks to this same native code in runtime. So yeah, this is some kind of time and space bending that you can do with Kotlin and some shenanigans with the build system. So yeah, what we have in native code, so basically without writing any C code, we have a possibility to reference pointers from C code, once again, without the hassle of needing to free it. Well, we will have to free it when the application stops, but yeah, they can just live inside this binary. So we have a pointer to a model, we have a pointer to a context, we have of the loaded model, we have a pointer of the vocabulary that can be loaded from the model, and we have a sampler that we can use to basically sample from the distribution generated by the model. And then, yeah, there are some things that we can use. Once again, you can use Kotlin, for example, even JSON to serialize, deserialize stuff to throw around the boundary between Java and native as pure strings rather than objects. Once again, it is some overhead, but as you can see, even on CPU, it works wonders. So once again, how we can utilize it? Let me check the structures. Okay, yeah, the structures not load. Yeah, it's loaded. So yeah, there are a few methods that we can utilize. I will not show some bigger methods to not intimidate people not familiar with C code. But for example, some method we can use to, let's say, yeah, just get the token from the generated, rather get a string from the vocabulary, or the string representation of the token from vocabulary. So as you can see, it looks like C code. Well, technically it is C code, but it is written with automatic memory management because we can use memscope functionality. We can automatically allocate native memory. Well, we can use some more manual approaches, but yeah, I decided not to because it's not needed. And you can easily call pure C functions as if it is Kotlin. So as you can see, I just call this function and it is not my function. If I go inside it, it is, well, a bit strange header that was generated by Kotlin Native, rather C-interops toolset. And as you can see here, I have the stubs for any native code I can execute. And well, I don't want to execute it, so I'll come back to this code. So as you can see, it is very simple. Like it works as C. Well, it compiles to the native bytecode, but you can use all the power of Kotlin. Like, for example, you can write suspend functions, so you can have async kind of operations, so you don't have to deal with native threading. You can use, once again, flows to generate streams of tokens. And here, for example, yeah, this is what I've done, for example, to generate text. So yeah, where is it? Generate text. So basically, we use a Kotlin construct, which is not available in C, but we can use it and just generate a stream of tokens as if it is some higher level language, though it will be compiled to native bytecode. So this is what we can use. And yeah, basically, as I said, if you remove all those spaces, etc., all the native code that is used, once again, if not including the GPU devices logging, I have slept on here. It is around 500 lines of code minus 100 lines of code of imports, because I don't like star imports, minus spaces. So technically the native side to run C inference takes around maybe 200 method stops. So once again, this approach is enough to start, and you can slap other things like key value cache management, context sliding windows, etc. if you wish, because all the methods are available. They are not important, for example, for simple operations. And for a demo purpose, yeah, this is just enough. So what else we can do with it? So we have a inference, basically, well, not framework, but rather runtime that can run on multiple platforms. And as you can see, it has been running on Windows if you want, or well, if not want, but I will show you how it runs on macOS, because I will show you the next thing. So what next we can do with it? So when we have an ability to run LLM locally without hassle on any device we want, we can build an agent. And once again, Kotlin allows us to do it in very concise and multi-platform way. And how can we do it? So basically, there's a thing that is called Cook AI. This is a fairly new agentic framework that is, well, similar to LangGraph, rather, that probably you have heard about. It has been developed less than 6 months ago, so it is also under heavy development, but it still already allows us to do different things. So how does it work? Well, basically, this is a pure Kotlin implementation that is mostly done in common code. So as I said, you can compile it to any targets that you wish. So you can compile it to a web browser, you can compile it to a Node.js runtime and everything. And out of the box, it has possibility to interact with all the popular LLM providers. But yeah, to that we'll return, because llama.cpp is not yet a popular provider. So what you can do with this framework? Well, basically almost anything you can do with LangGraph. So it has telemetry out of the box. It allows you to do tool calling. It has memory management. It can integrate with LangFuse and other Lang chain libraries. So yeah, it just works. And we can use it to basically add the functionality of agents to any cross-platform applications with, once again, even less amount of code that requires to build a native LLM inference engine to an application. So once again, what you can do with Cook? Well, you can build agents and provide the agent graph strategies that the agent will execute. So what is a Cook agent strategy? So basically, if you have done something with LangChain or read about it, this is kind of similar approach. You create nodes where each node represents some kind of agent operation. For example, here is a single run strategy that allows us to basically run and run inference and either call a tool and process the results or send an assistant message. So one of the most simple strategies that exists in the library itself. And you can build 3 nodes and then just draw edges of the graph between those nodes. So once again, syntaxes might be not familiar for Python developers with LangGraph, but still it is as easy. Like you will need to know a few functions that allow to forward the control flow between different nodes, and yeah, just use them. But this is a quite extendable thing, because you can create different nodes. For example, you can create customized nodes and even create customized strategy. Like, for example, you can have a node that allows us to just send messages or call a function to send messages back to the user. So we can get a feedback loop from the user. We can implement multiple and parallel tool calls, etc. So once again, to build the graph, you will only need to wire all the nodes together in a correct fashion. But in general, it will take you, well, about maybe 20, 30 lines of code, and you have an agent strategy. So what you can use this strategy with? Cook exposes the high-level AI agent function, right, that we can see here, that you can use in your Kotlin code, and it can be used in common code that is compiled to any platform. And this high-level function basically takes a few arguments. There are a bit more in general, but yeah, it takes an executor. So basically, who's gonna be doing the heavy work and calling all the APIs if needed. You can have the model parameters that you wish. You can define your strategy. If you wish, you can define a tool registry, once again, optionally, and not optional, but you can provide a system prompt. You can provide the amount of iterations the agent will do. And well, yeah, basically it's fairly customizable. And under the hood, this high-level function basically wires everything together and makes the strategy work. So what you can do with the strategy? Well, basically you can create tools which are also high-level constructs that you can make with Kotlin. And here's an example of what you can do. For example, you can extend from a already provided interface that provides a tool descriptor that allows you to specify some metadata of your a function. Then you can provide arguments, then you can provide the actual method that will be executed when this function is called. And basically, when you transform this tool into a part of LLM prompt, the Cook framework will serialize it in a correct way to present a JSON formatted tool description that can be used, and once again with all the information on like what are the required parameters, what are optional parameters, and stuff like that. Once again, this is a high level thing because, well, you will need a bit more lines of code, maybe like 5 to 10 more to set up all the metadata for the tool. But in general, yeah, this is quite high level and simple. And yeah, in the end, you can run it with your tool set, like for example, say, yeah, okay, you're a business agent and do stuff. Once again, you can do multiple agents, for example, different agent configuration per platform if you wish with the expect actual functionality. So yeah, this is once again a set of building blocks you can use and extend. Why I say extend? Because there are a lot of supported model providers. And well, unfortunately, local inference is not yet supported in general. And if it's going to be supported, it might support some other things like, once again, Google's Light RT or other things. So yeah, we can't use llama.cpp inside. Or can we? Basically, the only thing we need to wire any kind of large language model API into Cook is to implement a simple interface that already exists in the package. And yeah, I probably should remove all my drawings. And this interface is high-level wrapper around heavy-duty LLM calls, and it has one required method, which is called execute, to have a simple agent or rather LLM interaction. Basically, you provide a prompt, you receive a list of response messages to feed to the agent. The other methods, though very cool, like you can moderate your prompt for some unwanted language, you can wire execution of multiple tools at the same time, or you can even provide a streaming agent if you wish to have a more faster response from your model. But these three methods are kind of optional, like to build a simple agent, you only need execute. So once again, it does require a few lines of code, but to simplify how the method can be implemented. So once again, basically in my implementation, I just, when I execute, I just check if the model is loaded through a wrapper, or rather a binding, just clear previous conversation, convert cook messages to like my simplified format that I can throw over the native boundary if I wish. I call the wrapper to basically generate a response from a set of messages. If there are tool calls in the response, they are fairly trivial to parse using the Kotlin JSON parser, well, with some caveats, but still, well, as caveats depend on the models you use. But yeah, it's fairly easy and and anyone can do it. So yeah, well, one of the things or harder things is that yeah, you can or should build the prompts for the models you use. So yeah, you need to know, and yeah, someone's drawing all around. So yeah, probably not a good thing. But yeah, in general, it is easy to wire and build. So let's see how Cook can run an agent. I just press play and the magic would run. So yeah, hopefully it is not open on the same screen, but in general, yeah, have this little application. I can also select, let's say, a llama model. So my agent has access to quite some tools or data using the tools that I can use. For example, I can ask my agent for a borscht place for dinner, let's say. So yeah, we can ask the agent. It can generate some events, but in general, should be fast. So as you can see, the agent has generated a tool response, or the LLM has generated a tool response. Yeah, it has generated some processed data out of the tool response. And as you can see, it's kind of the same that we see here. So yeah, everything that was returned by the tool. And yeah, you can do things, for example, call other, like for example, list my yeah, probably a typo, but hopefully it will pick it up. Even the smaller models are smart enough to do it. If not, yeah, not really. But yeah, it is a small model, so um, we can specify a more exact thing that we wish to receive. Oh, okay. Well, it has broken because, yeah, it's a smaller model, but still, in general, with an like 80% probability, the agent will do its bidding or your bidding, and all it takes is basically a few lines of code. So once again, let's dive inside the code and see how it can be wired. So basically, all I had on the presentation is done in the project. So we can have an agent that has, once again, quite a lot of tools to search from, but the agent implementation is quite simple. So we provide a tool registry that the agent can use. Okay, so some are not used, but anyway, we provide a valid strategy that implements, once again, the same graphs that I described on the presentation, but you can use any valid strategy that you wish. And for example, we can have an exit tool to even ask agent to exit the conversation if it feels like, or you force it to. And yeah, in general, we just wire it up together with our provided wrapper that, well, probably we don't have time to see, some model configuration, strategy, tool registry, and system prompt, and that's it. So technically, to run an agent application in on device or on any device that can run C code, you need around maybe in general, 1,000 lines of code with imports, spaces, etc. But yeah, to make it actually appealing to users, you will need UI, and UI is not, so it is a main and the largest part of any application. It is unfortunately part of another story. Yeah, we will not discuss it today. So some final thoughts, because yeah, I see Victoria already saying that we should be done. So is it all production ready? So yeah, this is a kind of philosophical question, because even the widely used AI tools like LangChain, LangGraph are only coming to like release versions soon. So Kug, llama.cpp might also do it soon, but still, AI field is rapidly evolving, and you can already build applications, or as they say, you can just do things with the tools available. And as you have seen, it is not as hard. Like, once again, you don't have to write tens, thousands of lines of code. You don't have to write C code. You can use high-level languages with minimal API surface to run anything. And once again, this approach can be used even to wire Google's Light.RT, Microsoft ONX, or anything that has C or API. Basically, yeah, in all kinds of applications. And well, technically, you can use even WebAssembly to build web applications with both llama.cpp and Kotlin UI. But yeah, once again, this is something that we'll discuss when the web GPU support for llama.cpp is finalized and we can use GPUs from the browser. Until then, yeah, running inference in a browser with the CPU might not be a best solution. So in general, yeah, what else I can say? Well, thank you for participating. If you wish, or well, I will copy it. I will have a little rest from today's talk, and in like 5 to 10, maybe 20 minutes, I will push the final version of the project to this repository, and you can clone it, or run it, or do whatever. Or yeah, I will provide the links to Microsoft's and Google's store applications as soon as they pass final reviews. So you can see that this approach with minimal API surface, minimal amount of code written, can run literally anywhere. And technically, I have even used it on my older Android phone that, as I said, is not supported by Google, but CPU inference, well, let's say it runs slowly as hell, but it runs. So yeah, you can run it on a toaster even without UI. So thank you once again. I know that Victoria already has passed.
Yes, thank you, Dmytro. I think it will be a good idea to share those links in the chat in here so they
Yeah,
all
I
can
will do
have
it
it.
in a second. Yeah, so once again, I will
And
push the final version because it has some stubs that I have generated. And yeah, you can check it. Oh, I think
and
something happened, but yeah, in general, you
I'm
can do.
sharing, yeah. Sorry to interrupt you. I'm just
Yeah.
sharing again this feedback form so you can scan the QR, or I also share the link for the feedback form on the chat. It will be very nice to have all the attendees' feedback. So please, it takes less than 1 minute to fill the form. So we appreciate your responses in there. And then, yeah, I think we can open up to maybe some Q&A. If people have questions, they can put it in the chat as well. No
Oh.
questions?
Well, there is a question, what is advantage? Well, technically, Python can run on a server, Python can run on a local machine, but well, yeah, there are some frameworks that allow you to put Python in mobile applications, but yeah, they are not the best out there. So yeah, you will miss out on all some newer native features from the for example, iOS and Android ecosystem when they get released. So yeah, technically for server, you probably should not use it because Python can handle everything, and yeah, you can run it in like llama even if you wish. But to provide this approach, this approach provides you a way to basically ship AI applications to the platforms that can't run Python, or maybe for users that don't want to run Python because, well, all they know is like they want to click a button on their phone. But yeah, Python, well, once again, for llama.cpp, Python bindings probably are the best out there. Like they have those that are a bit outdated, but still they have the probably almost like 100% API coverage with like low to high level methods. So you can use it, well, as I said, to run even GPT OSS on your machine. So it might require you to build some drivers or download the pre-built versions for your GPU.
We have another question from Geronimo. Have you used?
Well, technically, well, I have tried React Native in general. Well, that's why I know that there are bindings, but yeah, I haven't used Flutter for quite a while, so I can't say anything about performance. But once again, according to the docs, because I read through the docs to get a few slides ready, they don't well, technically have a easy way to interact with native code. So unless you have like some already available libraries, you will have to write a lot of manual code, and it might not be as performant as you can do maybe with other technologies. But yeah, that's a just assumption because I have not worked with Flutter myself.
We have more questions in the chat.
Okay, there are a lot of questions. Well, technically, yes, there are a lot of questions. So yeah, well, first of all, from Andrei, well, technically, you, as you can see, have seen in the example, you can have an offline AI to work with personal data of users. There are a lot of, well, maybe in Ukraine, not all of them works, but in the other parts of the world, there are a lot of laws that direct developers on how can they use personal data, how they can store it, etc. And on-device inference will allow you to basically, well, not like go around those laws, but just not store personal data, so you don't have to go through all the hassle of conforming to the laws because it's all on device. Like the user has the data, you do not store it on your servers. So yeah, you can combine it once again, as Coog is a very advanced platform. It even can do a multi-agent orchestration. So you can build an agent, for example, that runs cloud inference. For some scenarios, you can build an agent as a local inference agent, and you can have a higher level agent that acts as a router depending on the user questions. So through, once again, the Kotlin technologies, you can build a combination of both if you wish. Once again, for the second question from Andrei, I really hope that soon we'll have something like from the Avengers and the Iron Man, so you can have a personal Jarvis assistant right inside your home or your phone that you can run locally, once again, without an issue. So yeah, I do hope that local inference will see more traction in the world. Once again, as we can see with Google, the Gemma 3N family that are made to run on even smaller devices. Google at least thinks kind of the same. So we can expect even more growth and maybe other model providers to build smaller models for on-device machine learning. And well, yeah, for your third question, like to balance privacy, yeah, you can use some filters. You can use a agent of agents to figure out which data should be sent anywhere and yeah, conform to the laws of the countries you ship your applications to. And well, hopefully I have answered your questions. So yeah, I will move to Daniel's. Well, technically, I have seen. So I have not used Kotlin like from the starts. I have started using it like since 2018, and I have seen quite good adoption, at least in the Android ecosystem, and with emergence and basically stabilization of the multiple platform approach. I think it will have a place in at least mobile development because, well, yeah, as I said, or web, mobile and web, because it has a lot of features that allow us to easily interact with, once again, WebAssembly, natives, native binaries and stuff like that, that require you to do some manual work on, once again, find some other person to do it and use his library on other platforms. So yeah, I do think it will evolve, and JetBrains as a company, they heavily invest in machine learning, or rather general AI things, like they have Kotlin that can run in Jupyter notebooks, like they have the Kotlin kernel, they have data science tools that can run on the Java machine and use Kotlin. Yeah, in general, they will push it and well, if they push it, and Google will help them, because Google, it tightly works at least through Android ecosystem with JetBrains. Kotlin will be, if not everywhere, but at least it will cover the mobile segment. So hopefully, yeah, my little explanation was enough for you, Daniel.
Well, thank you so much, Dmytro, for your time, for your explanations. We will be sharing recordings after the event next week, so stay tuned for receiving that email. We will be posting everything on YouTube. So thanks again for everyone to participate in today's session, and thank you, Dmytro, for your time and for your sharing your knowledge today. I hope you have
Have a
a good
nice
afternoon.
morning, I guess. So see you next time.